Consider now the weak form that we have defined. So as a consequence of subdividing our domain into two elements, so earlier this was between 0 to 1, now we have introduced an internal node. We're saying there are two elements, 1 and 2. So any integral between 0 to 1 will now be broken into two parts. One is from 0 to 0.5 and second is from 0.5 to 1. So this is just breaking down the definite integral into a domain wise integral. So first one defined here in element 1 and second one defined here in element 2. And doing this does not introduce any error because this is mathematically exact. So any definite integral of this type can now be broken into an integral within element 1 plus an integral within element 2. Which means if we consider this term, so that is now broken into this form. And for the element 1, which is from 0 to 0.5, we will use the approximation of u1, which is the definition of u of x in the first element, and also the definition of v of 1 in the first element. Okay. So you can review earlier that we had defined that u comma x was this vector minus 2 2 times d1 d2, and d1 d2 was the element displacement vector for the first element. Similarly, v comma x will be minus 2 2 times c1 c2, where c1 c2 is the element vector of arbitrary numbers for v of x. So basically this can be recast taking this c1 c2 transpose outside the integral because it doesn't depend on x, and within the integral we have this part. So this matrix comes because of the multiplication of these two vectors. Okay, and c1 c2 comes out common on the left and d1 d2 comes out common on the right. So basically we have c1 c2 times this matrix, which is defined for two nodes 1 and 2, times d1 d2. Similarly, for the second element, we will use the definition of u2 of x and v2 of x. Okay, and we can obtain a similar looking form where we have c2 c3 transpose times a matrix times d2 d3 transposed. The only thing is that this matrix here or this vector here is referring to the second and third node. And next we wanted integral 0 to 1, which was integral 0 to 0.5 plus integral 0.5 to 1. So this was the first element, this was the second element. So basically we want to add this and this. This plus this is what will give us the overall left integral, the total integral here. And when we add this, we notice that the terms with respect to the first node appear only in this matrix or in this form, and the terms with respect to 3 appear only here, whereas the terms with respect to 2 appear in both. So because of this addition, wherever you have terms coming from both elements or more than one element, these terms need to be added up. So this integral 0 to 1 ux vx dx, we have now this c1 c2 c3 vector, which is the full vector of c's, times and then on the right hand side we have the d1 d2 d3 vector, which is the full vector of d's, and in the matrix we have this, okay, which is in a way combination of matrix of 1 and matrix of 2. Okay, so if you really see, this first or the top block is coming from element 1, and this bottom block is coming from element 2, and wherever we have numbers coming from both the elements, these are being added up because we have to add them, because it is computing a definite integral into by subdividing it into multiple domains. Okay, and in the finite element lingua, this operation of concatenating two different matrices with appropriate addition is called the assembly operation. Okay, and you may see this term quite often in the finite element sort of texts. So basically we have this C transpose times a matrix, which is a combined matrix from the first and the second element, times the D vector, which is the full D vector. Similarly, we have the force term, the F term, and you may recall that there was no boundary, there was no body force, so L of x was 0, and hence we only had this V1 times 10 as the F vector. And now if you look at the first element here, the n1 of the first element and n2 of the first element are both 0 at this point, which is at the third point, which is x equal to 1, which is where we want the value of v at 1. Okay, so basically we have, this is v at 1 for the element 1. Both the functions have 0 value and they are being multiplied to 10. For the second element, this is the n1 of the second element and this is the n2 of the second element. Now n1 of the second element has a value 0 at 1 and n2 of the second element has a value 1 at 1. So in this case, now this becomes v of 1 for the second element and this gets multiplied by 10. Okay, so when we combine these, we get this, where this is 0 because in the first element this is 0, n1 is 0, this is 0 because this is 0 plus this is 0, and this is 1 because this is 1. So this becomes the F vector, and now we can combine it and write it in the weak form. So we have C transpose times a matrix times D equals to C transpose times a vector, and this vector C was arbitrary. So again, by using the logic of the fundamental lemma of calculus of variations, it is sufficient to say that if we are solving this system, which is again, if you look at, is of KD equals to F type, then we should be able to get what is D. The only problem, however, is that this cannot be solved yet. If you check, this matrix will come out to be singular. Okay, and I would urge you to think why this is singular. So why is this singular? I mean, there is a hint of the answer here, but I would suggest that before you move on to the next session, please try to come up with a possible reason of why this K matrix as we have formed here is singular, and of course if it is singular, this equation cannot be solved.